Welcome to this YouTube lecture. It's about 30 minutes, but split into two to help with uploading. The first half will be familiar if you have seen my fluid dynamics and PDM talks. The second half is new material on drawstring dynamics. The title is Drilling Process Dynamics Matters for Drilling Performance. It's about the problems that occur when what you see at surface is not what's happening at the bit. Let's take a step back and think about what is going on at surface and downhole when drilling a well. There are three processes underway. Fluid is pumped, the pipe turned, and the block lowered at surface. And the fluid emerges through the bit, and the bit turns and drills ahead. If everything at the surface and downhole is steady, the driller can normally understand what is happening downhole by looking at the surface sensors. But when there are changes at surface, or downhole conditions are changing, this is not the case. Surface sensors will be misleading. There are forces being applied at surface, at the bit, and along the pipe due to friction, and the material in the drill string responds to these elastically. Everything in the borehole is long and thin, and the forces are large, and what is occurring may not be obvious. Luckily, the physics of structures and fluids is well established, so correctly interpreted, surface sensors can still be used to work out what is going on. There are many examples of how dynamic elastic effects complicate drilling, so here are a few examples relating to all three drilling actions. The subject where compressibility has the most implication, and which is least generally understood, is the fluid flow and pressure inside the drill string, and I will start there. Looking at what happens downhole when the flow rate changes at surface, and what happens at surface when the pressure drop through a motor near the bit changes. Then in part 2, I shall move on to the relationship between bit and surface axial movement, moving the block. I will concentrate on depth measurement for logging well drilling. And then finally, something on rotation, and how ignoring rotational and axial compliance can lead to bit damage. But first, hydraulics. Let's start with what happens when the surface pumps go off, which happens every time there is a connection. These are theoretical curves, but they're pretty realistic, if a little smoother than reality. Everything is normalized here, so the flow rate has been steady at 1, and then, at time 0, surface flow stops. Though the surface flow stops, the surface pressure does not immediately drop to 0. Instead, it goes down in a curve over a finite time, which here is again normalized to 1. In one well, with 4-inch pipe, water-based mud, 10,000 feet long, the time was about 33 seconds. What about in the other direction, at the end of the connection? Pumps go on at full stroke rate at time 0. The surface pressure rises gradually. It asymptotes to its steady state value. In the same time it took for the surface pressure to drop to 0 when the pumps went off, the pressure is well below the steady state value when the pumps go back on. Why does pressure take so long to respond, and why the difference between pumps off and pumps on? The reason is that the fluid in the pipe is compressible. When there is flowing fluid, the pressure is higher due to the bit pressure drop and the pressure drop along the pipe, which compresses the fluid, so there is more fluid in the pipe when the fluid is flowing than when it is stationary. When the pumps stop, this extra stored fluid leaves through the bit. When you do the maths, it turns out that the fluid flow rate through the bit drops nearly linearly. Pressure is quadratic in flow, so the pressure at the surface drops in a parabola. When the pumps restart, it takes some time for the extra fluid to build up inside the pipe. If the system were linear, the two curves would be mirror images, but because pressure drops are quadratic, not linear in flow rate, they're different. In the time for the flow to stop and pumps off, in general, surface pressure is just over 70% of the final steady state value at pumps on. What kind of timescale are we talking about here? The answer, of course, is it depends, but usually the time for the flow to stop will be from a few seconds to about a minute, depending on the drilling parameters. For one real well, it was 33 seconds. As the drill string gets longer, the time gets longer, a bit faster than linearly, as the pressure in the pipe is also increasing, as well as the volume of fluid. It is proportional to the volume of fluid, so if the inner diameter of the pipe is larger, so the time increases. Oil-based mud is more compressible than water-based mud, so the flow stop time is also longer. It does depend on the mud, but somewhere around 50% longer. Finally, for the same drill string, the time grows linearly with flow rate. If the surface flow rate is only changed a small amount, the downhole flow rate change is a low-pass filtered version of the surface flow rate change, where the filter is just a simple one-pole filter. A one-pole filter looks like this, also called a forgetting filter. At each time step, a small proportion of the downhole flow is forgotten, and the same proportion of the surface flow added in. The time constant in this is the flow stop time. This is the time that governs how fast the whole hydraulic system can respond. So why does this matter? Well, one reason is that if the flow near the bit is varying, then the mud pulse measurement while drilling telemetry signals are also varying. And the mud pulse MWD transmissions will have more errors and be more difficult to synchronize. The longer the time to stabilize, the longer it is going to take to reliably get an error-free survey to surface after a connection. Can this be speeded up? Yes, it can. In this graph, you see the effect of the pumps going from 0 to 1 at time 0, and I'm plotting the flow rate through the bit and the surface pressure, both normalized to their final steady-state values. Time 1 is the time it would take for the flow through the bit to drop to 0 if the flow was steady at 1 and the pump stopped, which is shown in the dashed line. There is an extra parameter here, and that is the ratio between bit pressure drop and pipe pressure drop, and in this example the two pressure drops are equal. Changing the ratio will change the shape of the curves a bit, but does not change the method I am going to describe. The curves from the previous graph are dashed. The solid lines show the bit flow rate and surface pressure using a fast start. The flow stabilizes in roughly 1/3 of the time, close to the flow stop time in this case. The way this is done is to start with a higher flow rate than the final drilling flow rate. That way, the stored fluid gets into the pipe faster. Any higher rate will speed the process up. Here, I've used 20% higher, and somewhere between 10 and 25% is a good rate to choose. The trick is to drop down to the steady state drilling flow rate once the pressure hits the value it will have at steady state, which is known from the previous stand's drilling. Here you see the surface and bit flow rates, together with the surface pressure. Any flow rate overshoot helps, and rig crews may be nervous about using high flow rates, so start small and see that the pressure never gets too high. When I first came up with this method, I thought some calculation and possibly automation would be needed. But it has been tested and turned out to be easier than expected. Just watch the pressure dial and drop the flow when the pressure hits the mark. There are situations, for instance, with a small difference between pore pressure and fracture initiation pressure, where normal practice is to stage up the pumps, starting up flow at a low level to break the fluid gel before increasing the flow rate. There are 2 points to make here. Firstly, at the last stage, when the pumps go to full rate, fast start can still be used to speed things up. Secondly, if annular pressure can be recorded near the bit, the different pump and rotation initiation procedures to break the gel can be experimented with in situations where there is no danger of fracturing the wellbore, to see how annular pressure spikes can be avoided while still minimizing startup times. And of course, in all those other situations where the pumps are not being staged up, you could always use fast start. That was the implications downhole of what was happening at surface. What about the other way around? An important source of flow variation near the bit is a downhole positive displacement motor, a PDM, also known as a mud motor. When we choose a PDM to drill with, we use the charts that come from tests that have been made on the motor in a dynamometer, in a test chamber at the manufacturers. The test apparatus mimics the motor in the hull. There is a pump driving fluid through the motor, which exits through nozzles similar to bit nozzles. There isn't a bit cutting rock, but instead a friction pad, which is pressed against a very well held down resistance in order to generate the torsional load. Between the pump and the motor will be a few meters of hose. For a variety of flow rates, the load is varied, and the pressure drop across the motor and the motor rotation speed measured. The test generates graphs like this. This is for a realistic but fictitious motor. On the right, you see that torque is close to linear with pressure, and it also depends very little on flow rate, so that is not shown. The crucial lines are the ones on the left. Although at zero load, the motor rotation speed is proportional to flow rate. As the pressure increases, the motor rotation speed drops as more fluid leaks through the motor, until the motor stalls. It doesn't rotate. Repeated motor stall will damage the elastomers in the motor, reducing its ability to function. Crucially, the motor stall pressure is lower for lower flow rates. I'm going to tell a little story, which is based on a field example. A starting point in choosing a motor would be, what is the highest torque the bit might see in a transient, and how much pressure might that generate? Say that for the rate of penetration and bit we want, the maximum transient bit torque will be about 12 kilofoot-pounds, giving a pressure across the motor of 1000 psi, which is acceptable for the surface system. Checking on the rotation curves on the left, with the planned flow rate of 300 gallons per minute, although the motor will slow during the transients, it won't stop. Based on this transient limit, the steady operating point for the motor is chosen as torque of about 6 kilofoot-pounds, with a differential pressure of 500 psi, giving plenty of headroom for transients. The motor is run, and there are lots of transients, but they are all at about 300 psi above steady state, so an apparent differential of 800 psi. We should be fine. But well before the end of the bit run, it is clear that the motor is misbehaving. And when it is pulled to surface, the elastomer condition shows that it has been stalling. So what happened? I've heard it said that motors don't behave the same downhole as they do in the dynamometer. Is that what's happening here? Here is a diagram of the motor in its configuration during the drilling of a well. There's a couple of differences with the dynamometer. There's a bit, not a friction pad, but the important difference is that there are thousands of meters of fluid in a pipe between the pumps and the motor. If the system is in steady state, then the fluid in the long pipe in the well and the short hose in the dynamometer behave the same. But that's not the case for transients. Sound in drilling fluids normally travels at between 1000 and 1500 meters per second. So if pressure increases across the motor, it takes time for the effect of that to go up the pipe and for the pumps to respond. There is the same delay again before the effect of the pump's response reaches the motor. This is seconds later. So short torque transients may be over before the pump response even reaches the motor. Before the pump response arrives, the pump is invisible to the motor acoustically, and the pipe may as well be considered as infinite. When acoustic waves move along pipes, both pressure and volume flow rate vary. They are proportional. The sign of the proportionality depends on the direction, and the amplitude is the acoustic impedance, given by the sound speed times the density, divided by the fluid cross-sectional area. Let's see what happens when there is pipe above a motor at the end of a drill string. Start with the situation before transient. There is a steady state flow rate, capital Q, and the pressure drop through the bit is proportional to Q squared, proportionality K. There is also a pressure drop across the motor of D due to the load on the bit, giving a pressure drop through the whole system of D plus KQ squared. Now, if there is an extra torsional load on the bit, it creates an additional pressure drop across the motor of capital delta. This is going to generate a transient pressure wave heading up the pipe, and the pressure and flow are related, so there will be a transient flow rate change too, minus Q. But how big will that be? If the flow through the motor drops by lowercase q, the flow through the bit is now capital Q minus lowercase q, and the pressure drop through the bit is K times the flow rate squared. And the transient pressure change above the motor is the transient pressure change across the motor, reduced by the amount that the pressure drop across the bit has decreased due to the change in flow. In order to calculate what that flow change is, and the change in pressure above the motor, we need to apply the proportionality between pressure change and flow change. When you put in typical numbers, these effects are significant. Drops of flow rate of between 25 and 50% are normal, and reductions in apparent change in motor differential pressure of a similar order or larger. To recap, there are two linked effects, both of which are important. The transient flow through the motor is less than the previous steady-state flow, one consequence of which is that the change in pressure across the motor is higher than the change in pressure above the motor, which is what is seen at surface. Here is a numerical simulation from a full drill string and motor model, including axial and rotational motion of the drill string, as well as fluid acoustics. At 0 time, there was an increase in bit torque, which resulted in a 400 psi increase in motor pressure drop, which disappeared a few seconds later. This graph shows the motor pressure drop versus time. The sharp spikes are from rotational waves going to the surface and back. Now add change in pressure above the motor from the same simulation. You can see that the peak has been reduced by a factor of more than 2. You can also see the effect of fluid reflections and the long tail that is the low-pass filtering effect. The flow through the motor is reduced by about 40% during the torque spike, storing fluid which is then released when the torque reduces. So let's go back to our original example. This is the steady-state operating point. And this is what the driller believed to be happening. Pressure transients of about 300 psi, which should not have stalled the motor. But in fact, the pressure transients across the motor were higher, because not all the change is seen above the motor. And while the steady-state flow rate was 300 gallons per minute, the transient flow rate was below 200 gallons per minute, so the motor stalled. The motor was behaving exactly the same downhole as it was in the dynamometer. The difference was the thousands of meters of compressible fluid between the pump and the motor. These are the implications of understanding this phenomenon. Firstly, in motor selection, the flow effects of torque transients need to be factored into choosing a motor and the steady-state drilling parameters, so the motor will not stall when normal transients occur. And secondly, when monitoring drilling, any pressure spikes should be interpreted correctly, allowing for the difference between the transient pressure across the motor and the transient pressure above the motor. I have a whole hour's lecture on PDMs in my drilling dynamics course, so if you want to know more about PDMs and dynamics, that's where to go. And now that's the end of part 1. Now, I recommend you watch part 2, with examples from drill string dynamics.